Nikki. So welcome to this introduction to LaTeX. So as Nikki might have alluded to, I personally think that LaTeX is basically the most beautiful thing ever. And once you have experienced its wonders, you will never want to go back to the dark, murky depths of Word ever. So hopefully by the end of my talk, you might be about that. So just to give you a bit of an outline, I prepared some resources to go with this talk, and I'm going to run through those first. Then we're going to talk about what LaTeX is and how and where we can use it. And then we're going to discuss its many different functionalities. I'll be covering many of the common things you might want to do in LaTeX, and Nikki's going to follow up with some additional functionality descriptions in her talk. So as I said, I've created some resources. So the text files in resources contain examples of all of the functionality I'm going to cover in this talk. So if you want to, you can pull these up and you can look at them alongside this talk, or you can download them at your leisure to look at afterwards. So the links are on the slides. Nikki is going to just stick those in the chat for you as well, so that you can easily get to them. So for those of you who have already got Git installed and have followed the prerequisite instructions, if you feel inspired to download these from Git, then you can clone the repository that I've made, which is the GitHub link on the slide. However, if you don't want to do this yet, or because you haven't actually learned how to do it yet, because that's going to be covered in Sam's talk, then they can also be downloaded from the zip file on the AI3SD website. So the prerequisites folder just has the installation instructions for this workshop, in case you were downloading it from the website and you wanted to do that first. The Hello World folder has the Hello World example we're going to work through first, and the examples folder has some individual example files, so you can all see the small code snippets of the different things I'm going to be teaching you. And then there's a big example.tex file which has a fuller explanation of all the different examples together, which I'll give you a bit more detail about at the end of the examples. So to start us off, what is LaTeX? It is essentially a document markup language. Now, for those of you who tuned into our talks on research data management 2 weeks ago, you might remember that we talked about different ways of creating documents. There are WYSIWYG editors, aka what you see is what you get, such as Word and Google Docs, where you immediately see what your document will look like when you type something in. LaTeX, however, is a little bit different. For those of you who might be familiar with web programming, it's somewhat similar to that in the sense that websites have HTML code and CSS styling behind them. And what is actually behind the website is not the same as what you see, because the browser renders it into the web page that the developers wanted you to see. And LaTeX is a bit like that. You code the markup of your document, then you compile it to create a PDF, and that PDF then follows the format and styling instructions that you've given it. So the first thing you need to do to use LaTeX is to download and install it. So I won't go into this in too much detail, as you should have already read and followed the prerequisite instructions that you were given upon registering for this talk. But for anyone watching this later, the instructions can be downloaded from the link on the slide, and they're also in the main repository and zip file of the resources that I produced for this talk. Once you've downloaded and installed LaTeX, you need to decide what IDE you're going to use. For anyone who's not familiar with the term IDE, it stands for Integrated Development Environment. So as I said in my instructions, if you're feeling particularly brave, you can edit your LaTeX in a text editor, or even in the terminal using a VI editor, which you'll see Sam using later in our GitHub demo, and compile it via the command line. Or you can create a makefile. So makefiles are basically just files that define a set of commands to be run, and they're typically used to compile programs or indeed LaTeX documents from their source. If you are going down the command line route, I would recommend making yourself a makefile, or you can find examples of good ones for LaTeX. I have linked to a good example on this slide. Just because compiling LaTeX can be quite complicated, you often have to run the commands a few times, and once you compile it, it creates a lot of auxiliary files as well. And in your makefile, you can automate running all of these commands, and you can run some cleanup commands to remove those aux files just because they're created as part of the compilation process. So some people absolutely love this stuff, myself included, obviously. And I had so much fun writing LaTeX and VI and making my own makefiles when I did my computer science undergrad. But equally, it's not for everybody. There are plenty of decent LaTeX editors out there. And I will say generally, as I've moved on to work on much larger documents, as I did actually write my entire thesis in LaTeX, I've tended to start using an editor. So my preferred editor of choice is TeXworks, as I've noted in the installation instructions, which actually has a nice, simple, handy play button on the slide, which I've shown on the slide, and you can just press that and compile your LaTeX. But there are a whole array of LaTeX editors, and there's a link listed in the prerequisite instructions if you want to look at different ones and decide which your favorite one is. But all of the examples I'm going to show you moving forward have been done in TechWorks. So let's start with the most basic of examples. So for those of you following along with the files, please open helloworld.tech and helloworld.pdf to see both the files from these pictures in action. So when you learn programming, the first test program you'll write in any language is typically something to print out the words hello world. And we're going to do just that. So on this slide on the left, you can see the LaTeX that I've used. And on the right, the result of hello world being printed to the PDF document. As when you compile your LaTeX, you can see what the PDF it generates will look like. So let's unpack this a little bit. So the first line states our document class. All LaTeX documents must have this. If you try and make a document without this, it will not compile. The text in the square brackets are options that are passed to the document class. So in this instance, this is that the text should be 10 point and that the document size is A4 paper. And there are a number of different options you can have here. In the curly braces, it states the document type. There are also many different types of document types you can have. Some of the common ones are report, book, letter, etc. And then we have the begin and end document commands that you can see in green. Again, you always need this. These define where the document starts and ends, and anything in the middle then relates to the document. So basically, what I just showed you had all of the core required components of the document structure. So this slide just shows you an outline of the different concepts that make up a document at its base level. So as discussed before, we start with the document class command, provide whatever options you want, and you set the class, which is the document type. The bits that come next to the preamble. On the slide, you can see the words use package. Nikki's going to talk to you about packages later on, and I'm going to touch on a few of them in my examples. But essentially, if you want to do anything above the basic sort of inbuilt LaTeX functionality, such as insert some special mathematical symbols, pictures, funky tables, then you'll need to insert the correct packages. So these essentially just import the code required to enable you to do the tasks that the package was written for. So for those of you who code, this is basically equivalent to importing a library. Everything to do with the packages can go in this preamble bit, or if you're using a lot of these, you can make a separate style file, which Nikki will cover in more detail in her talk. Then we have our begin and end document commands, and inside that then goes the text and any associated commands with the document content. For those of you who want to read more about this, at the bottom of the slide, I've linked to a good source of documentation, and Wikibooks is just an absolutely fantastic resource for LaTeX, and I will be referring to all the relevant links for the different examples throughout this talk from Wikibooks. So now we're going to move on to some examples of the different things you can do in LaTeX. If you're following along with the resources, please navigate to the examples folder and open up sections.tech and sections.pdf. So as you can see, if you want to make headings, you can use the section command. So typically these will go down 3 levels. So section, subsection, and subsection. There are some packages you can get that allow you to go further, but from a decent writing style perspective, I would encourage you to think about whether this is really necessary if you did find yourself looking for that. But the left-hand side shows the examples of how to do those commands. They're very simple, literally just \section for your top level, subsection for one down, and subsection. If you were to go on, you would just keep adding subs. And as you can see from the right-hand side, the headings then get put in. They are in incrementally smaller bits of text, and they are automatically numbered and subnumbered. So you don't need to do any of that. It is basically equivalent to doing the headings in Word. You just have a bit more control over them, and they don't start flapping around and getting confused if you move around between styles. So a natural lead on from headings is creating your table of contents, because essentially this uses the information from your headings to build a table of where your different document sections are. So making a table of contents is really simple. You literally just need the command table of contents, and it will build you a table of contents noting where all the section headings are. So you can see on the slide, we've same example as last time, but above our headings, because we want the table of contents to come first in the document, we've got that table of contents command, and then you can see that it automatically builds you that contents on the right-hand side. Obviously, this is an example document, so all the headings on page 1, but they would obviously be in different places if this was a larger document. Just as a side note, sometimes LaTeX might need to be compiled more than once to get the full information to build the table of contents. So just be aware of that if you are looking at doing this manually and you're compiling it, you might just need to press the button more than once. So don't panic if it doesn't appear immediately. So next is paragraphs and line endings. This might look complicated, but it's actually not. There are just a few different ways you can do this depending on your stylistic preferences. So paragraphs in LaTeX by default will indent. You can use both the par command or simply leave a blank line, and that will just create a new paragraph on the next line that's indented. If you don't want to indent, personally, I hate indenting. I'm not sure why, I just do. But then you can use the new line command, which is 2 backslashes. So this will start a new paragraph on the next line that is not indented. And if you want a blank line between your paragraphs, you can use 4 of those. I mean, in reality, you can just keep adding those as well. Ultimately, the thing to remember here is that the par command in the blank line will by default lead you to an indented paragraph, whereas using new line commands won't. However, going back to where we talked about packages, and if you don't like your paragraphs indenting, which personally I don't, then you can add command, which is something else you can do alongside packages that you can put in your preamble. And Nikki, again, will talk a bit more about commands in her talk, but you can literally just set the command I put in red on the slide, which just says, don't indent your paragraphs, basically. Because if you have large documents, it generally is advisable to make sure you split them out by blank lines so that things are quite readable. So if you want to have lots of paragraphs and you don't want them indented, I'd recommend adding in those commands. And these just different combinations of paragraphs can be found in paragraphs.tech. So you can just play around with those and see what different things happen. The next thing I'm going to touch on is text formatting. So this is pretty simple. If you want bold text, then you can surround that text by \text BF. If you want italic text, that's very similar. You surround it by text IT. And if you want it underlined, then you can just use underline. You can also chain all of these commands together. So as you can see on the left-hand side of the slide, I've shown you using all the separate commands, but there's also one where all 3 of them are used together, and that produces bold, underlined, and italic text. It's just as simple as that. You can do it in any order, any combination or sub-combination, and it will highlight, it will change your text to be what you want it to be. And the examples for this can all be found in textformatting.tech. So you can also make different types of lists in LaTeX. You can make regular bullet pointed lists, as is shown at the top of the slide. So these are done using the itemize command, or you can make numbered lists using the enumerate command, which is the one in the middle. And as you can see from the slide examples, they are basically coded in exactly the same way, just one uses the word itemize and one uses the word enumerate. You can also nest your lists. So here I have an example of a bullet point list with sublists inside it. You can nest either way, so you could nest a numbered list in a bullet point list. I'm not really sure why you'd want to, but you could. And possibly more usable, you can also nest a bullet pointed list in a numbered list. All of these different examples can be found in lists.tech. You can keep nesting, you can add as many items as you want. You just need to make sure that you enclose it with your begin and end command for either itemize or enumerate. One of the common mistakes is either forgetting to close it or just absentmindedly forgetting to close the bracket around one of your items. But yeah, so you can do lots of nice things with lists. Now, we're going to move on to the slightly more complicated matters of figures and captions. So there's quite a bit to unpack here. So firstly, if you want to add in an image, you need to use the graphics package, as this imports the code you need to pull in your figures. Then actually coding the figure has several different aspects and options. So firstly, you use the begin figure command to set it up, and there are various options you can pass it here that will determine where the figure should sit. So I couldn't resist putting these in because this is one of the things I like to mention to people if they ask me why LaTeX is better than Word. I'm sure all of you are familiar with trying to move images around in Word or insert images in Word, and your entire document just goes to hell and everything is in the wrong place and everything is moved around and you don't know what's going on anymore, and it's very upsetting. LaTeX is much easier to deal with than this when it comes to images. You have a lot more control. So I just wanted to share this table with you, which was taken from the Wikibooks documentation on figures, and it shows you the different float commands. So generally I tend to use HT because H will try and default it to roughly the position it is in your text in the first place, and T will default it up to the top of the page. So just to show you again with a bit more detail here, you can see that I've got begin figure on the slide and HT next to it. So that's me setting the float options and saying basically try and put it as close as you can to where I put it into the text as possible. So there are then a bunch of other options that you need to set. So the include graphics command is where you actually define getting the image in and the size it should be. So I've got two different examples of setting the size. So the top example shows you that I'm saying that basically I want it to be 95% of the line width of the page. Whereas the scale one, I've set it to 0.1. You might be thinking that 0.1 actually sounds quite small, which it does. But if you look at the images folder, which is included in your resources, you'll see that this is actually quite a big image. So whereas you can set things to be a percentage of the page width, the text width, that will obviously only be based on that width. If you scale them, it's based on the actual image size. So for example, if you have something that's like 2000 pixels, then you're going to have to use a very small scale. So it can be advisable to shrink your images a bit before putting them in. Now, size is really important here because this will determine whether your image actually ends up in the correct place. So unlike the insanity of word image placement, generally your LaTeX image will either end up where you've told it to go, if it's small enough to fit in the gap on the page, or if it isn't, it will generally default to the next place it can fit into. So if it's just too small for the current page by a little bit, it will go on to the next page, easy enough to find, easy enough to fix. If it's massive, so for example, you haven't thought about your scale or you've just whacked it in at the size it is and not thought about that to start with, it will probably go to the end of the document because it will be potentially too big to fit into any of your spaces prior to that. But good news, either of those are super easy to fix. So if it doesn't appear where you want it to go and you have followed the commands correctly, you can probably just assume it's a size issue. So you just need to play with the sizes. If it's a little bit too small for the page, just make it slightly smaller, or you can just force a new page and then it will go to the top of the page. So once you fix your size issues, then in the curly braces, you can see I've got images/salem.jpg. So that is the file path. In this instance, images is a folder that's at the same level as the text document we're in. And then Salem is in that images folder. So that's why I put that file path in. Obviously, if it was in several folders up or several folders down, I would need to put the correct path in for that. But you basically just need to link it to the source of the image. Then finally, we have the caption. So this can just be set using the caption command, and then that comes printed underneath the image. Much like with sections, LaTeX will automatically number the figures for you. So you don't need to worry about that. You'll always get figure 1, 2, 3, 4, 5, etc. with whatever captions you've given it. And if you then, for whatever reason, choose to move your images around, again, it will automatically renumber those in the correct order for the document. So there's quite a lot of nuances and different things you can do with figures. So I do really recommend reading the WikiRich documentation thoroughly if you're trying to do things more complicated than just putting a picture in. So tables, again, these can be a bit tricky, but they're really easy once you get your head around them. So this is just a very basic table. You can use the tabular package, and in the curly braces, you define the table spec. So this just involves specifying how many cells you want and how you want them to be aligned or sized. So here we have used L, which means automatically size the cell and align it to the left. You can choose center or right, or you can specify the exact size you want, and I'll show you that when we touch on advanced tables. The vertical lines that we've got around the L's, they specify whether you want the cells to have grid lines or not, like down the columns. So one vertical line will give you the sort of border we've currently got on the table. You can have 2 as well if you want doubles, or you can have none if you don't want to show all of the border lines on your table. As we covered earlier, we've also got the double slash lines. So those normally they denote the end of a line, but in this instance, they denote the end of the table row. And then your H line tells it to draw that horizontal line. So that's the horizontal border of the table. So for this table, we have 4 borders. So there's an H line at every row end. Then we have the ampersands, and the ampersands just define new cells. So I've deliberately tabbed these out so that you can see them in order, because then it looks a bit more like a regular table. I tend to format my tables within a document like this, so it's easy enough to see where each column is and potentially identify any problems. So the code that I've put here for this can be found in basictables.tech. There's a lot of different options for tables, so it is worth swatching up on some of the documentation. But I'm just going to talk you through some of the slightly more advanced things we can do. I mean, I'm not going to go into too much detail because I probably could have talked for an hour on tables by themselves. But if you look at the advanced tables.tech, you can find an example of some of the additional table functionality. So as you can see for this example, you can have merged cells, something you're probably quite familiar with doing in both Word and Excel. So we've got the Aristocat cell on the left-hand side of the table. This has been merged using the multi-row package. Similarly, you can do things in multi-column as well if you want to merge across your columns. So as I mentioned on the previous slide, the horizontal lines and the H line denote the table lines. And here we've chosen not to have an H line right at the top, and therefore we've missed out, and we've also missed out the vertical lines at either side of the table. So then you can see that we now are missing that sort of almost top three border lines. The cells have also been specifically sized. So remember I said we could do left, center, right, or a specific size. So using P, curly braces, and a number will specifically size that cell. That can be quite useful if you've got a lot of data and you're trying to cram it into a smaller place, and then you're trying to define how much space you want to give each one. And sometimes it isn't always as advantageous to have them all equally spelled out. So for the eagle-eyed among you, you might have also noticed on the third line down the table, I've used a C line rather than an H line. So C line is your friend if you're trying to merge anything across your rows, because whereas H line will draw a full horizontal row, C line will draw it from the start and the end of the cell points you tell it to. So in this instance, it just misses out that first cell. So that's really, really useful. And you can do all numbers of column and row merging. So you can also add more functionality by wrapping the tabular environment in a table environment. So you can see an example here that we've got the table environment round the tabular environment. And this allows you to specify the float, which is the overall alignment of the table, and also to add a caption, much like we did with the figures. I mean, basically everything that you can think of that you could do with a table in Word, you can probably do it in LaTeX and make it look prettier. You can have tables that span multiple pages. You can change their orientation, color, format the text in them, color their cells, use symbols, do all the merging. So the example of this table can be found in advancedtables.tech. And again, I do really recommend reading all the documentation thoroughly. As Nikki pointed out to me, because I have never thought to look for this sort of functionality, you can also use websites such as LaTeX tables, and that will allow you to either import an existing table you've got in a CSV, or to build your table using a WYSIWYG editor, and it will automatically create the LaTeX code for you, although it might still need some tweaks. Personally, I do quite enjoy making them myself, but I appreciate not everyone does, and particularly if you've got a really large table or quite a complicated table with, you know, various mergings, etc., then it could be really, really useful, and you'd get the majority of that code printed out for you. So, as you may have noticed from the markup, LaTeX uses a number of common symbols as part of its main markup. I've noted some of the most common ones on this slide, and there are two ways of handling this. So if you want to use those characters within the text yourself, you can escape those characters using a backslash, although unfortunately that doesn't actually work for the backslash itself. Or you can use special commands to print the symbol. So for example, the code for a backslash is a backslash text backslash, which is shown in the example on this slide. There are also a number of special commands for all other symbols. So whether that be access on letters or currency signs, you can also use different alphabet sets, potentially some imported via packages, or there are quite a lot of default symbols as well. And I have actually listed in the examples.tech, there is a link to a list of all of the symbols and the codes that have been somebody nicely read all the documentation for. Now, one of my big bugbears about people who do LaTeX wrong is LaTeX has a slightly different way of handling quotes. So often the double quotation mark is not interpreted correctly. And then you end up with your quotes looking back to front. So I don't know if you can see, I don't know if I, no. So in the detailed the details up on your examples, it will actually show you some of the quotes being incorrect. Basically, the left-hand side ones end up upside down, and this looks really, really wrong. Once when somebody asked me to proofread their report, I circled every single one of them and pointed out that they didn't look correct. She wasn't very happy, but I did show her how to fix them. So good news is these are quite easy to fix. So instead of using the normal double quotes either side, on the left-hand side, you use 2 back single quotes on, and then you just use your normal ones on the right-hand side, and then a back and a right of each for single quotes. This is really important if you're copying and pasting stuff in, because typically sometimes you can get your compiler to recognize the straight quotes and it will be interpreted correctly, but normally if you've copied and pasted it in, it will have the angled quotes, and then LaTeX will interpret it wrongly. So you can find these examples in quotes and characters.tech, and I've added in the list, I've added in a link to the special characters documentation into that documentation as well, and that has that really comprehensive list that I mentioned. So hand in hand with our special characters is mathematical symbols. So one of the things you might have heard about LaTeX is that it is a bit famous for being a lot better at handling mathematical equations than Word, because you just have a lot more flexibility to code them in. There are certain symbols shown above that you can use just the keyboard for if you're trying to display an equation. So they're the ones in red on the slide, and they can just be typed directly into the document. For anything else, you need to use special codes. So you can do a ton of different things in LaTeX using the math packages and the inbuilt math functionality. You can write equations, matrices, you can show fractions and square roots. Again, whatever you can think of, you can probably do it. And there are also just different shortcuts for going into math mode. So if you want to do anything that is beyond just using those normal symbols, then you need to go into math mode. There's, for some reason, I'm not really sure about, 3 different ways of going into math mode. Those are all displayed on the slide in green. They all do exactly the same thing. It's just your preference for how you want to format it in your document. Sometimes if you're doing a huge chunk of code, it can be nice to use begin math and end math, and then it's very obvious. If you're doing something really small in your text in your paragraph, then it might be nice to use the other 2 just because it's a bit more succinct. So here's just a few examples of some of the different things that you can do in math mode. Again, there are so many different things you can do. It's really worth reading up the documentation for the types of equation you want to do, because chances are it's just going to be a case of, okay, I need to have these symbols. You go and look up the codes for all the symbols, and then you can just put them together. So I put a few examples here in the slide. And most importantly, if you look at the one on the bottom, powers and indices, that also shows you how to do things like subscripts and superscripts. That can also be used in regular text as well, if you just stick something into math mode. If you were trying to just talk about the power of something through a document, or even if you were literally just doing a different type of sub or superscript as well. But as you can see from the examples on the left, I've used the main math mode, but you could have used any of them. And then I've just coded in the different symbols, and in the instance of the one at the bottom, the different commands for super and subscript. And then you can see on the right hand side, that's what you get. There is so much documentation out there and so many examples of things. So if you don't know what you're doing, just go and have a search for it. Another really great thing you can do with LaTeX is you can cross-reference things using the label and the ref commands. So this is really, really simple. As shown on the slide, you can just put the label command right under the heading that you want to reference, and then you use the ref command where you want to refer to it. And as long as you use the same label the same sort of label that you've given it correctly, that you put in those curly braces, then LaTeX will automatically call the number of the section into your text. And again, that's really great, because if you move things around, it will automatically keep that reference because it's referring to something you've labeled rather than just an arbitrary number. So this simple example can be found in labels.tech. And you can also label and reference your figures and tables. So with the figure, you add the command into the main figure bit under the caption. And then in the tabular environment, you need to actually, similar as we talked about earlier wrap that tabular in a table to be able to label it. It's the same as captioning it. You need to be able to wrap it to be able to label it. And you can add the command in near where you put the caption. You might have also noticed, if you're paying lots of attention to the slide, that I tend to specify what type of label this is in the name. So I've used sec for section and fig for figure. And that's not necessary, you don't have to do it, but it does help you to keep track of what it is, particularly if you have a massive document like, say, a thesis that has tons of figures and tables and sections that you will need to be able to refer to. So all of these examples have been covered in examples.tech and examples.pdf. So an important note, because I got a bit extra making these, whilst in the individual example files, I've just put commands in for what we were talking about. So basically the examples that I've shown you on the slide, but you've actually got the files you can play with. I've structured the example document a bit differently. The PDF has full instructions on how to use all the commands we've talked about. And in some instances, it shows you the code and then the output result. But I have actually marked up the text document to make this PDF. So if you open up the text document, you will see a fuller example of a LaTeX document, because you'll be able to see how I've done all of the formatting and how I've displayed all the code to show you what it looks like in the PDF. So I really hope that this will be a useful resource to you. If you are super interested in LaTeX, take it away and study it and have a look and play with it. As I said, it can all be downloaded off GitHub or the website. So I just wanted to talk you through a bit of troubleshooting. LaTeX is wonderful, but it was also written by computer scientists for computer scientists, and it doesn't always have the most helpful of error messages. So I'm just going to run through a bit of general guidance for this. Firstly, try and avoid needing to troubleshoot. If you compile your code regularly, then you will realistically know what you've just changed. So if you've only written a couple of lines, you've written one table, you've imported one figure, you compile it, it goes wrong, you can be pretty sure that's the problem. However, if you've, and we've all done it, I mean, I've definitely done it, you confidently write on several sections ahead, feeling great about yourself, 4 images, 2 tables, and then you get around to compiling it. If something goes wrong, it might not be as obvious. So also check for special symbols. So particularly if you're copying things in from Word documents, it's not just quotes, that won't break it even if it looks wrong, but the amount of times a straight ampersand sign will come in and obviously break it because that's a special character, or a percentage sign, that's a good one, then that will completely break your code. So you just need to be aware of those. Check that you haven't tried to end a line where you shouldn't end one. So although usually your error messages will be quite clear about that, because it will say there was no line to end here. For figures, your sort of classic mistake is generally to mess up the image path. So just make sure you know where your images are. And for tables, it can often be missing out or adding in too many ampersands. And overall, remember that Google and Stack Overflow are your friends, much with coding. Search for the error code and search for the messages, because even if they aren't super clear, chances are somebody else will have had it, and hopefully have at least posted enough information about it to help you understand what the problem is. And finally, some general tips. Obviously, as I just said, compile often. Secondly, reuse your code. If you spent ages making a pretty table and looking up how to merge your cells and your columns, etc., then maybe save a copy of this table. Record the packages you've used for it. So next time you need to do something like that, you can go back to it. Also keep a list of your favorite packages. If there are things you always tend to use, like the graphics package, I use that in everything I've ever done. Maybe keep a record of those and a file of those so you can drop them into any new document. Use an editor that allows syntax highlighting. This might not sound useful, but for anyone who codes, you'll know how useful syntax highlighting is, because as you might have seen from some of the previous examples, things like the begin and end commands, they are green, they come in a different color. Generally, your comments will come out in red. So you can see different things in different colors, and then it might also help you be aware if something's gone wrong, because something will be in a color that it shouldn't be. Also have cheat sheets. There are so many commands, you can't be expected to remember them all. I certainly don't remember them all. So there are loads of really good ones that can be downloaded. I've got a link on the next slide, or you can make your own if there are certain things you know you just tend to forget. Lay out your document neatly, because it all might be fine having a couple of paragraphs, higgledy-piggledy, just some backslash lines between them and a table that's all jumbled up if it's like 2 or 3 columns. But as soon as you get into a big document, if you need to be able to go through and figure out how to edit that particular document, you might make lots of changes to, like a thesis or a journal paper. And also, certainly if a lot of you are working on it at once, you really need that to be well laid out with lots of order, so that you can look through it with almost as much clarity as you would, say, the Word document. It's not quite WYSIWYG, but you want to kind of be able to see what each section does. And then it's much, much easier to troubleshoot and just to figure out where certain bits are. And finally, make use of the documentation. So the wiki that links I've been posting have really good documentation for pretty much anything you could want to do with LaTeX. And also just look at Stack Overflow, look at forums, look at Google. Chances are there are plenty of people who've come up with whatever obscure thing you want to do and posted about it. So it's always a really good resource. So onto that, useful resources. So as I said, highly recommend Wikibooks. Overleaf, which Nikki's going to talk to you about, also has a really good resource on learning LaTeX. I've put a note to a GitHub, to a LaTeX cheat sheet that is on GitHub, because that's really, really useful. And I've also linked you to Stack Overflow with the questions that are tagged with LaTeX. Stack Overflow is great. There are so many LaTeX posts on there. So I appreciate this has probably been a super whirlwind tour into LaTeX, and I could have gone on for hours, and I think I've just about made time, but hopefully you have an idea about some of the many different things you can do with it. I really hope the resources are useful to you and provide you with a good starting point.